The above example says, suppose y squared equals 5 times x squared. Differentiate both sides with respect to t to get an equation that describes how the rates are related. So we have an equation that describes how x and y are related, and we want to know how are dy dt and dx dt related. So this is just practicing differentiating with respect to t. Okay, so in this case we have y squared is equal to 5x squared, and we want to just differentiate both sides with respect to t. So this time we have a little bit of chain rule involved. Here, remember, y is a function of t, so the outer function is y and the inner function is the dependence of y on t. So first differentiate the outer function, and we have 2y, and then multiply by the inner, which would be dy dt. And on the other side do the same type of thing. The outer function would be x and the inner would be the function that the relationship between x and t, which we don't see in this equation, but we imagine that it's there. Okay, so differentiate the outer, and we have 2 times 5, that's 10x times dx dt. That's because we're differentiating with respect to t. Now, if you want, you could imagine, I'll just put this in parentheses, or I'll just do this on the side here. You can imagine that this is written in the following way: y of t, in other words, this is a function that depends on t, squared equals 5 times x of t squared. So in other words, here we see the outer function and the inner function. Here the outer function is parentheses squared and the inner function is y of t. So differentiate, bring down the 2, and subtract 1 from the exponent, and then multiply by the derivative of the inside. That's where that dy dt comes out. And here 2 times 5, that's 10. This is the derivative of the outer. And then derivative of the inner is here, dx dt. So this is the same thing we wrote on the left-hand side, except we didn't use that, oh, sorry, let me just get rid of that 2 over there. We brought the 2 down and subtracted. Okay. There. So just condensing this, since we don't really write y of t, we just write, like we had on the left here, we just write 2y dy dt is equal to 10x dx dt. So that's how we write that. Okay, so this is just an exercise in differentiating with respect to t. All right, sometimes what we do, just practicing leading up to these related rate problems, sometimes what we do in related rate problems is we have 2 variables that we're interested in. Let's say, again, I'm calling them y and x. And the third variable is z, that's sort of just in the way. We want to find the relationship between dy dt and dx dt. In this equation, we have a z that we want to get rid of. So we have an equation, a second equation that gives z in terms of x. X is the variable that we are interested in. So what we do is first get rid of z, or all right, substitute for z, then differentiate. So that's a pattern. That's what we usually do. Differentiate with respect to t. Okay, so let's do that. So we're going to do the step of substituting for z. So we have y is equal to 4x squared. And here, remember, we had z equal to 3x. Y is equal to 4x squared, z squared. Let me write it out again. Z is equal to 3x. So we're going to take that 3x and we're going to put it right here instead of z. So here's the substituting. Y is equal to 4x squared times 3x squared, which is equal to 4x squared, times 9x squared, which is 36, x to the fourth. All right, so we have y is equal to 36x to the fourths. So here we wrote that without, now we have a relationship between y and x, z is removed. And so now we're ready to differentiate with respect to t on both sides. So let's do that. On the left side we have dy dt is equal to, and here we have 4 times 36. So that's 144. 4 times 36, subtract 1 from the exponent, x cubed, and continue with the differentiation. Remember, x is also a variable that depends on t, and we're differentiating with respect to t. Okay, so that's that. That's the relationship between dy dt and dx dt right here. In these examples, we just want to practice differentiating with respect to t. So here we have equations with variables x and y, and we want to differentiate both sides with respect to t. Okay, so let's do that. Let's practice. In number 1, we have y is equal to 5x, and on the left we have dy dt, and on the right 5 times dx dt. Okay, let's go to the second example. Here we have y is equal to 5x squared. So on the left, differentiating again with respect to t, we have dy dt is equal to 5, bring down the 2, 2x, times the derivative of x with respect to t, times dx dt. All right, so that's 10x dx dt. And we're doing these problems in order to build up to the skills that we need in order to do related rate problems. So these are typical computations that we do in related rate problems. Okay, number 3, we have x squared plus y squared is equal to 25. Okay, and again we want to differentiate with respect to t. So here we have, we're going to do a little chain rule here, 2x times dx dt, and same here, 2y times dy dt is equal to 0. Derivative of 25 with respect to t is 0. And finally, let's look at that last one, number 4. All right, in number 4, we still want dx dt and dy dt, some equation that gives us the relationship between dx dt and dy dt, but we have a z in here. So but we have an equation that tells us that z is equal to 2/5 x. So what we're going to do is first use this equation to get rid of z from this equation, and then we'll be able to differentiate with respect to t and get dx dt and dy dt. So let's do that. So first we have y is equal to 5xz, and now z is equal to 2/5 x, and we're not really interested in z, so we want to get rid of z. All right. Okay, because we only want dx dt dy dt. So do that substitution, and we have y is equal to 5x times 2/5 x. All right, so these cancel, and so we have y is equal to 2x squared. And now dy dt is equal to, here we're going to differentiate 2x squared with respect to t, bring the 2 down, and we have 4x to the 1 times dx dt. Okay, here we have our first typical related rate problem, and this one says, and typically we have some sort of word problem, and from this word problem we're going to get an equation and differentiate it with respect to t. That's the usual sequence. So this one says a square on a computer screen is increasing in size. So we're going to picture something like this, a small square, let's say on your computer screen, and it keeps getting bigger. So it's changing, its size is changing with respect to t. All right, so that's what we're going to imagine. All right, continuing with the problem, the length of the side is increasing at the constant rate of 20 millimeters per second. All right, so let's say that here's the square. Let me just make it look more like a little bit more like a square. And let's say x is the length of the side. So we're told that the length of the side is increasing at the constant rate of 20 millimeters per second. So that means that dx dt is equal to 20. All right, so that's the information that we're given, the rate at which it's increasing. All right, in the second sentence it says find the rate of change of the area. All right, so what we want to do is we want to find dA dt. That's the rate of change of the area of A, if A represents area, when x, the side, is equal to 100. When x, that's the side, is 100. All right, well, where's our equation? We want some sort of equation that relates our two variables. One variable is x, and the other variable is A. Well, we know the formula for the area of a square is side times side, or in this case, x times x. So here's our equation that relates a and x. And now we want an equation that relates dA dt and dx dt, because we want an equation with dA dt in it. We want to find dA dt when x is equal to 100. So we want to differentiate with respect to t. Okay, so let's do that. So we have dA dt is equal to, and here we're going to do a little bit of a chain rule, 2x times dx dt. All right, so we can finish the question. Find dA dt when x is equal to 100. Okay, so now we're going to sub x equals to 100, and we have dA dt is equal to 2 times 100 times dx dt. And we're told here that dx dt is always 20. So this is 20. Okay, so now we can answer the question. dA dt is 2 times 100 times 20. So that would be 4,000. And what are the units here? Let's see, it's millimeters and seconds. So this is the rate of change of an area. Area is measured in square units. So that would be millimeters squared per second. Since it's a rate, it's going to be per, some unit of time. So that's the answer to the question. Okay, here's another related rate problem. In number 2, it says the radius r of a circular oil spill is increasing at the rate of 20 feet per hour. Okay, so we can picture an oil spill that's a circle, and it keeps increasing. And it says the radius, let's say here's the radius. It says that the radius is increasing at the rate of 20 feet per hour. So we're told that dr dt is equal to 20. Find the rate at which the area is increasing when r is equal to 1,000. So we want to find dA dt, that's the rate at which the area is increasing when r is equal to 1,000. Well, again, where's our equation? We want an equation that relates our two variables, radius and area. Well, we know what the area of a circle is. The area of a circle is pi r squared. So that's our equation that relates a and r. And like in the previous example, we're going to differentiate with respect to t in order to answer the question, finding dA dt. So we take this, take the derivative of both sides with respect to t. So on the left we have dA dt is equal to pi, and now a little chain rule, bring down the 2, r dr dt. Okay, and so we want to find dA dt when r is equal to 1,000. So now we're going to sub r equal to 1,000 in order to answer the question. So we have dA dt is equal to, let's see, I'm just dividing this. Okay, I'm just separating this, the right side, from what I wrote here. dA dt is equal to 2 pi, r is 1,000, dr dt, and we were told that dr dt is 20. So this is 20. Okay, so dA dt when r is equal to 1,000 is equal to 2 pi times 1,000 times 20. So that's 4,000 pi. And what are the units over here? Well, let's see, the units are feet per hour. So we're talking about area changing. Area is measured in square feet, so that would be square feet per hour.